So, as it was seen, especially in the indicator diagram for both the spark ignition engine and the compression ignition engine, what's taking place inside the cylinders is quite complicated from a thermodynamic point of view. There are many models that have been developed in order to describe from a thermodynamic point of view what is taking place, and in this chapter we will see three different theoretical cycles that can be used in order to describe both of these engines. These theoretical cycles are quite simplified in order to make it not too complicated to calculate what is going on. And here I will present some assumptions that are done for all these three cycles that will be studied in this chapter. So, first big assumption is that we consider that inside the cylinder we have a standard fluid. So we don't take into account the change of chemical nature of the fluid that is due to combustion, and we consider usually that this standard fluid has the same thermophysics properties as air. This is not a bad approximation, because most of the fluid is anyway dinitrogen, that is the main component of air. This is implying several other things. So one thing we do is we consider that the standard fluid behaves as an ideal gas. That's a good assumption for us, because it will allow to use the ideal gas law, but this is quite right anyway for the type of gas we have inside the engine. We'll also consider constant properties, and this is doing some approximation, because there are very large differences of temperature between for example, the end of the combustion and the beginning of the admission, and so here we will neglect the change of properties, either due to the change of chemical nature or due to temperature. Also, due to the fact that we just consider a standard fluid, we don't consider any change of mass inside the cylinder. This is especially for the compression ignition engine, where some mass is added due to the fuel injection at the combustion stage, and here this change of mass is neglected, and it is not a very bad approximation, because anyway the mass of fuel that is injected is very small compared to the mass that is already present inside the cylinder. So those assumptions will be always done here concerning the fluid that we have inside the cylinder. Now, concerning the transformations. For the compression and the expansion, this transformation will be taken as reversible and adiabatic. Reversible is close to be true, because these transformations are not very far from being reversible. But adiabatic, as it was discussed before, it's not true at all, because the motor body is usually cooled down. So there are other motors that can take into account this heat transfer using polytropic transformations, but this will not be done during this course. We'll do the big approximation to consider the compression and expansion reversible and adiabatic. Then we'll consider the combustion to be adiabatic. This is adiabatic in the with the same kind of meaning that when we consider a heat exchanger to be adiabatic. In fact, we consider that the heat that is released by combustion is not transferred outside of the system, but kept inside of the system. So the heat of combustion will be just taken as a heat input to the fluid that will be used to increase the pressure and temperature of the fluid during the combustion. Then, maybe the most complicated assumptions, maybe the most complicated to understand, is that the four-stroke engine will be described thanks to two-stroke theoretical cycles. In fact, the admission and exhaust strokes will be completely replaced by an imaginary transformation, which is an isochoric cooling. So to understand a bit the concept behind this theoretical transformation, here we consider that there's no change into the nature of the fluid, and usually the admission and exhaust transformations are open transformation where the mass inside the system is changing. Here we replace this by this transformation as if the fluid at the end of the expansion was brought back to the same state that we had at the end of the admission. So in fact, the fluid will be just cooled down to the temperature it has for the admission, and this imaginary heat transfer that we have for this cooling corresponds more or less to the heat losses due to the high temperature of the exhaust gases we have in the engine. So, doing this approximation that you will see in the theoretical cycles, it means also that we don't consider the pressure losses that were highlighted during admission and exhaust. This is again an approximation, and because the theoretical cycle are only two strokes, we consider that we have one theoretical cycle every 2 rotations of the crankshaft, because we cannot just double the number of cycles with this modeling. So that will be the main thermodynamic assumptions that we will do for all cycles, and then we will add specific assumptions for each of the cycles.